Welcome to another video of biology. In this video, I want to talk about this paper, Beyond Neural Scaling Laws, Heating Power Law Scaling via Data Pruning. The paper is published in 2022, August, by Meta AI researcher and Stanford University and Tübingen University. So basically, this paper is talking about the scaling law and beyond that. And first of all, we need to know what is a scaling law. So let me give you an example. So when we have a model, we know based on different research have been done from 2015 by AlexNet, and after that, we found that if we increase the model size, we can improve the accuracy. And in other research, we found that if we increase data size, we can improve accuracy too. So these are coming from the concept of scaling law and power scaling law. And the reason that it's called power scaling law because uh, based on the experiments, we know that this improvement in accuracy is following the power function. So just want to give you an example, power vs exponential scaling, for example. So if you want to compare these two, so you see uh, this is an example of power x2. So, and this is an example of exponential improvement. So this is another good example that you can see. So if we have some sort of exponential, we would be beat the power uh, scaling law. So if we have some rules that we say by applying this rule to the model or to the data can get exponentially better. So it's outperforming our scaling law and can beat that. So they mention here that if we prune the data somehow with some rules, some metrics, we can beat the power scaling law and become to and make this progress to be like exponential scaling law. And that would be awesome because increasing the model size is usually uh, needs power, needs money, and not available for all researchers. And increasing data size is not available. It's costly because it needs more annotation, and sometimes it's not possible in some, for example, in medical application to get more data on a specific task. So data pruning strategy, if it can outperform previous scaling laws, uh, would be promising. So I want to walk through the paper. I think this figure I have created here just for explanation that how we want to do this uh, data pruning based on the paper. So basically, we have a data and we have a model, and based on this, we want to train a model to improve our metric. Data pruning strategy depends on the initial dataset size. So usually in a data, we have some example of easy example. We can say, for example, if it is ImageNet and you're classifying dog and cat, some dog's picture are really typical. So we can say that dog example is easy for the model. Some example are hard. Sometimes differentiating between cats and dog, if the picture is captured somehow, or maybe that breed is something hard to distinguish, so that we can categorize those examples as hard example. The paper mentioned here that if the initial dataset size is small, it's good to prune harder example because it can give us a better model and more robust model. And if the initial dataset is large, it would be good to apply more hard example to the model because we already have lots of easy example that can model learn on that. And for pruning, it better to prune some of the easy example to have a balance of hard and easy example. But how we know, problem is how we know this data is easy or this data is hard without any labeling. Because if you want to apply this kind of data pruning, we need another round of annotation to find out this data is easy by annotator. Maybe even we need some agreement between different annotators. So that would be difficult. So they provide a way of unsupervised or self-supervised learning for giving a rank to this data. And based on the prototypical example, I will explain that in a little bit. So let's back to the paper. I mentioned here widely observed neural scaling laws in which error falls off as a power of a training set size, model size, or both, have driven substantial performance improvement in deep learning. This is exactly what we've talked so far. However, these improvements through scaling alone require considerable cost in compute and energy. Here, we focus on scaling of error with dataset size and show how both in theory and practice we can break beyond powering law scaling and reduce it to exponential scaling instead if we have access to high quality data pruning metric that ranks the order in which training example should be discarded to achieve any prune dataset size. So it is exactly what I was explaining so far. So the cool parts start from here. We then test this new exponential scaling prediction with prune dataset size empirically, and indeed observe better than power law scaling performance on ResNet trained on CFAR10, SVHN, and ImageNet. So there's another point in the paper that I want to discuss it. So not only related to this model that we can make it better, they also talk about transfer learning. So if we have pre-trained this model and we want to do it and we want to transfer it for another task on another data, they mentioned here that prune this data that we are already pre-trained that model as much as possible, then transfer it, accuracy can be improved. Also, they mentioned here that when we have a transfer, there are two parts here. First, we prune the data for the model that we are pre-training on it. And another is that pruning data for the upstream task that we wanna uh, train on it. So I'm not sure the upstream task is a good word here, but if we have another data set, so I can call this data number 1 and I call this data number 2. So they mentioned here if we have this model, we transfer it, and now we want to fine tune this model based on the new data. They mentioned if we can prune this data to have a better quality, we can gain same performance when we apply the whole data. And they mentioned something interesting about 10% of the data can be used here just for fine tuning, and that 10% data can achieve same performance when we fine tune it on the whole data. Same thing happened here. If we um, prune this data and only you train this model on 10% of the high quality data, then we transfer it and train this model, we can achieve the same performance, and that's amazing. So let's back to the paper. You mentioned here, given the importance of finding high quality pruning metrics, we performed the first large scale benchmarking study of 10 different data pruning metrics on ImageNet. Find most existing high-performing metrics scale poorly to ImageNet, while the best are computational intensive and require labels for every image. We therefore develop a new simple, cheap, and scalable self-supervised pruning metric that demonstrate comparable performance to the best supervised metrics. Overall, our work suggests that the discovery of a good data pruning metrics may provide a viable path forward substantially improve neural scaling law, thereby reducing the resource cost of modern deep learning. So consider, for example, Chat GPT or GPT or any other models that use a very large data set. So by pruning data, by make the data uh, somehow with a high quality example, they can train maybe even smaller model. They publish some sort of teacher student training uh, for pruning even model, or better say distillation of the model, while pruning the data, and they could achieve the same performance and sometimes even better performance. So that would be very awesome that everyone in the AI domain independently can train their model without need for GPU. So let's come down here. They're talking about these different things about neural scaling law, easy example, hard example that I've explained here. You can read the paper. I just highlighted some parts. For example, they mention here the optimal pruning strategy change depending on the amount of initial data, as I mentioned. With abundant initial data, one should return only hard example. And if we have small or scarce initial data, we should return only easy example. So another thing is that they mentioned exponential scaling is possible with respect to prune dataset size, provided one chooses an increasing path to optimal pruning fraction as a function of initial dataset. So we will talk about this a little. So let's look at these because these are important. I think authors are getting inspiration from these kind of method, and they have implemented their self-supervised learning based on this, and also the method SWAV, swapping assignment between views, SWAV, a method of self-supervised learning. So good to know how we can, back to this question, that if we have this data, how we can say without any annotation, we can say this is easy example and this is hard example. And then we can rank those data. So first of all, there is a EL2N score. So they mention here, for example, trained a small ensemble or 10 different ensemble network for a very short time, about 10 epochs, and computed for every training example the average L2 norm over the error vector. That's why it's called EL2N. So it's the expectation of L2. Data pruning by retraining only the hardest example with largest error enabled training from scratch on only 50% and 70% of CFAR 10 and CFAR 100 respectively without any loss in the final test accuracy. So with this kind of scoring, so look at it again. We have 10 different models and we have ensembled them and we just train them for 10 epochs. And for every training example, we calculate the average L2 norm of the error vector. I think that n maybe return back to this number of network. Each network, I think, create a L2 norm, and we calculate the average of L2 norm for each example. And if, yeah, it's like aggregation of different annotator. So look at this. Let me write it here. So we have different kind of models, and for example, in this case, 4. And we have an example. This is an example. We already trained these networks based on the ensembling method, and this is the output of these as error. So we apply this example to the whole network, and we calculate the average L2 loss, L2 norm of the error. And based on that, if all of the network saying that error is high, so this means that this example was hard for training, so we can give it a score. So based on that, they prune the data, and by pruning, it means that based on the initial dataset size, I think they pruned the hardest example. They mention the performance of EL2N on image that has not been explored yet. So that would be an opportunity for next research. Another one is forgetting a score and classification margin. This is interesting. You mentioned number 8. Notice that over entire course of training, some examples are learned early and never forgotten, while others can be learned and unlearned and forgotten. They develop a forgotten score, which measure the degree of forgetting of each example. Intuitively, example with low forgetting score count out of as easy example. So if we say something is not being forgotten during the training, so it is easy. If it is something is forgotten repeatedly, it's hard. They explored data pruning using this metric, but not as ImageNet scale. So there is a problem with this method. Let me explain it this way. So we are training a model, and each time we are applying a batch of data or one example, and we calculate the loss. And after some iteration, some constant value as checking out the forgetting value. So we have a buffer here, and for each example, for example, every n iteration, we go and apply those examples to the model and see model could learn those or not. Very similar to Ensemble one, but this is just one network, and during the training, we just look at this. And based on how much loss we can get from them, and maybe there are some sort of, I'm not sure about that paper, I haven't read that, but suppose that these batch of data is just applied 3 epochs before. So it's like we can have a plot like this, that during the time, how much uh, example one is forgotten by the network. And time is also a factor here, that if we train it like some previous epoch, or if we train it 100 epochs before. So if it is still recognized by the model, that would be an easy example. But for example, if it is like 3 epochs before and the loss for this example is high, so it means that this is a hard example. And based on that, they prune the data, and they mentioned here that by this pruning, uh, they could get a better performance. We can look at this paper in the future. Just put in the comment that you are interested in one of these. Another one is memorization and influence. I have the influence paper in my list. I will talk about it in future, but that would be good. So they defined a memorization score for each example, corresponding to how much probability of predicting the correct label for the example increases when it is present in the training set relative to when it is absent. A large increase means the example must memorize. So if we have a model and we have a data set, these are the example. So I can create some example, very simple, for example, suppose bootstrapping method. So I can create another version of this data set, but I just, suppose this is training data, just making this more sense. So suppose I create a new version of this data, but I do not have this example, and I train the model and see for that example, can model learn that or not? And they mentioned here how much the probability of predicting the correct level for the example increases when it is present in the training set related to when it is absent. So another time, we um, add that data. I bring this here. So I'm just talking about this specific example. So this time I bring this here. I train the network and see when I apply this example, how much difference I will get. So they mention here a large increase in the probability of predicting the correct label means that example must be memorized. This, the assumption is that after I add this to the training set, there is a high chance that it is, for example, in this case, the model cannot predict the correct label, but in this case, because we just passed this, it could. It means that this network somehow memorized this, because based on the other example, we should somehow understand that this example could produce a specific output. But when we don't pass it as a training, the model cannot estimate the output, predict the output. So this example can be a hard example in this case. They mention here, remaining training data do not suffice to correctly learn this example, as I mentioned here. Additionally, they mentioned an influence score that quantifies how much adding a particular example to the training set increased the probability of correct class label of a test example. So they create another metrics that each example we will have, let me have a buffer here. We will have a buffer here that's showing each example, for example, this example, how much influence one has, that if it is presented in the training set, how much influence it has in predicting it. They mention here low memorization and influence score correspond to easy example that are redundant with the rest of the data, while high score correspond to the hard example that must be individually learned. They did not use this score for data pruning as their computation is expensive. We note since memorization explicitly approximates the increase in test loss due to removing each individual example, it is likely to be a good pruning metric, so it does not consider this interaction. So they didn't use this method for pruning data. I think they just used that for understanding the uh, influence of each example. So another one is ensemble active learning. And ensemble active learning is um, active learning iterates between training model and selecting new inputs to be labeled. You know, the active learning is somehow like, let me explain a little bit about active learning. So if I have this model, I'm just explaining a simple way. I think I have some video related to active learning and how that works, but this is just a review. So active learning is like I have a annotated data, but this is very small set. And I train a model and I have this model ready. So model performance is not still good because I still don't have a good data set. So we add more example to this, but these are some of them are not annotated. So this is not annotated, this is not annotated. And we apply this to the model and we get there. This is not for training this time. After we train this model just by the annotated data, we have a version 1 of the model. Then we apply other example and we get the confidence score of that model. And by getting those confidence, we know that model is sure about something and not sure about others. So usually we pick low confidence example and we just choose them for annotation. And by doing that, we are increasing our chance that model improve itself for predicting the higher confidence output. So uh, research showed that picking a specific example for training, if you suppose we already know what is the influence of an example, so we can add it to the training because that can improve the tested accuracy. In this case, for example, we are just focusing on confidence or other metrics that we can look at it like the distribution of data or stuff like that, but that's the whole story of the active learning. So they mention here, um, active learning iterate between training a model and selecting new input to be labeled. In contrast, we focus on data pruning. So this is in contrast with active learning because in active learning we're adding data, but in pruning we're removing them. So one-shot selection of a data subset sufficient to train to high accuracy from scratch. A variety of core set algorithm have been proposed for this, but their computation is expensive, and so data pruning has been less explored at the scale on ImageNet. And nearly clustering approach allowed training on 90% of ImageNet without sacrificing accuracy. Notably, reduced this to 80% by training a large ensemble of network on ImageNet and using ensemble uncertainty to define the difficulty of each example. Exactly what I was talking about. So they just train 80% of the ImageNet on the network, on the ensemble network, and they use the uncertainty, or you can say the confidence level, to define which example was difficult and which example are hard. We will show how achieve similar pruning performance without label or the need to train a large ensemble. Another example is diverse ensemble. Um, They said assign a score to every image in ImageNet given by the number of models in diverse ensemble that misclassified the images. Intuitively, low score correspond to easy example, and the pruning performance of this metric remained unexplored. They didn't establish a method for pruning. They just have a diverse ensemble. This is very similar to method first, EL2N, but they are just evaluating the misclassified images. So as a summary, they mention only one of these metrics have been tested for efficacy on data pruning at a scale. And all of these metrics required label information. There is no theory of when and why data pruning is possible for any of these, and none of these work suggests the possibility of exponential scale. If we go back to the first problem that we had was we have a model and we want to beat our scaling law by pruning data. So what they are assuming here is based on the prototypical example. If you look at the few shot learning papers or even meta learning, you will find some good elaboration about prototypical example. I'm just giving you some idea. So if we have a data set and we somehow get a representation of it, for example, using autoencoder, and we using some method like TSNE or stuff like that, we just map the representation in the space, in 2D space. So we will have different example. Let me just create. So for example, we are classifying dog and cat. And when we have an autoencoder and we represent the data in two-dimensional space, suppose we have a good representation learning. So in this case, suppose these are the green one is related to cat and these one are related to dog. If we cluster this data, so we will find two center for these two clusters. Suppose this is the center of this cluster, and similarly, this is the center of this. My prototypical example are examples that are more close to this center because they are typical. They are in the center of the cluster. Look at this, for example, it would be example prototype example of the clusters, but there are criticism. I don't want to go through the details, but some of the outliers, center of the outliers clusters, that would be a criticism example that's usually hard for train or hard example. So we suppose this typical example as easy example. To compute a self-supervised pruning metric for ImageNet, we performed k-means clustering in the embedding space of ImageNet pre-trained self-supervised model. Here is, as I said, swapping assignment between vector. They already have prototype vectors as some codes. They said here, define difficulty of each data point by distance to its nearest cluster centroid or prototype, as I mentioned, what is the prototype? Thus, an easy example or the most prototypical. Yeah, that's it. They're showing here an example of the heat map. These are hard example from the memorization. If you remember, the memorization is what they have explained, and this is the self-supervised prototype that they have used using SWAV. You can see these are easy example because they are just zooming on the animal for the classification, but these are hard example because usually they are multiple or maybe is effect of water are making problem for the model. So that would be interesting to look at those hard and easy example from perspective of the model. In the paper, they have lots of formulation about how they have learned the teacher-student model for data pruning and also and model distillation. So we don't want to go through those detail, and I think that's enough for this paper. Thank you for your attention. Please subscribe. 90% of the viewer are not subscribers. Please subscribe, leave a comment, and share with your friends.